actually the last slide. So what I was mentioning is that now that we have assessed the challenges and opportunities, what's the next step? What should be done in the CPS industry in order to move it forward and achieve the goals set by the IPCC? First, we have to work on R&D and to increase efficiency, like decrease the energy penalty and make it more cost effective. And we can also implement large scale in order to drive costs down. The more facilities and the larger the facilities we have, the costs will go down from the learning by doing and the economies of scale concepts. And as I mentioned, we should implement CCU to create financial incentives. We should work more on policies. We should spread awareness among people. And finally, we should couple this technology with renewable energy, because if we ever want to reach negative emissions, we have to completely forget about fossil fuels and start to shift towards a more renewable energy powered world. And thank you.
Okay, thank you, guys. Can you please go back to the first slide?
Yeah. This one?
Okay, yeah. I will tell you when to stop, okay? Move down, please. You should number your slides, guys. Every time I tell you number your slides.
Yeah, man. Who here? It's better on the left.
Yeah, nice. Move down, please, Pat. Slide 16.
16?
16.
Yeah.
Okay, Radi, can you please explain in summary what is happening here?
Yeah, so basically post-combustion, as its name indicates, is that we take the CO2 after burning the fuel. Now, usually we burn fuel to get out of it heat. That is what fuel is mainly used for. So when we burn the fuel, some heat is generated. This is what we use. And we have byproducts, which are known as flue gas. The flue gas is then taken. This is where the CCS starts. The flue gas is taken to an absorber tower, and we are implementing what we first defined as chemical absorption. We introduce this solvent. The solvent gets the CO2, it absorbs it, and then we are taking this solvent CO2 solution to a stripper tower, where the stripper tower separates the solvent from the CO2, and then we get pure CO2 to compress it and then store it.
Okay, and in slide 20.
Oxy-fuel. Okay, so the main difference here is that the separation of CO2 and of H2O. Here we don't have a solvent. Only the flue gas is CO2 and H2O. And here a simple condensation can do the job, separating the CO2 from the water. And we finally get pure CO2 to store.
Okay. Can you move down with the slides, please?
Yes.
Okay. Before. Slide 27.
Yeah.
Jad, can you please explain the main difference between these three techniques?
So it's basically 4 different techniques, but the last 2 we can put them together. Someone has to mute. Hello. Okay.
Yes.
Yes, doctor, can you please mute your mic?
Yes.
Okay, thank you. Okay, so the first one is structural trapping. It's the most macro scale, where basically we trap the liquid between porous and non-porous rocks. Then we go on a smaller scale, which is residual trapping, where the CO2 is trapped between the rock grains. This is also a physical sort of trapping. The solubility and mineral is no longer physical. It becomes more of a chemical sort of trapping. CO2 reacts with H2O and gets dissolved in it to give HCO3 minus, which then reacts with the minerals to form MgCO3, which permanently holds the carbon in place. So it becomes solid and it's held in place for forever, basically. So this is basically the difference. It's like we're going on smaller and smaller scale, and the first two are physical, the second two are chemical.
Okay. Can you move down, please?
Yeah.
Can you move down with the slides? Okay. Yeah.
No, this is the end.
Okay. Previous slide. Go back, please. slide 30. No, go down, please. Okay, previous slide. Slide لحظة شوية شباب. 1 minute.
Sorry.
Slide 34, I think. 34.
34 about financial incentives.
Yeah. So can you talk more about financial studies performed and what were the results obtained?
This slide basically tells us that CCS is not profitable because there is no generation of revenue. It's only cost, like it's negative cash flows if you follow a engineering economy perspective. So only negative cash flows do not give the encouragement to investors to put in this money because they are getting the carbon and putting it underground. So like, what's the added value here? What we're suggesting is to shift to a CCU technology, which basically utilizes the carbon instead of storing it. So this is not negative, net negative, but it is net zero.
Okay. Okay, thank you, guys.
Thanks, Professor.
Hope you enjoyed the presentation.
Yes, it's fine. Thank you. Okay, who's next? Hadi and Jadi already?
Yes, we can go now.
Yeah, let's start.
Yeah, let me share my screen.
Yeah, share your screen.
Okay, can you see it?
Yes.
Okay, so hello everyone. Our presentation today is going to be about smart grids. We're first going to introduce you to what they are, then we're going to explore smart grid technologies, their future state, and their current state and future outlooks. So, the increase in world population and the associated economic activity, along with technological developments, led to a fast-growing increase in the demand for electricity. And to maintain equilibrium, this increasing demand must be accommodated by an appropriate electricity infrastructure. This infrastructure is not only restricted to electricity production means, but it also involves the management, supervision, transmission, and distribution of this produced electricity. And in this framework, the electrical grid plays a central role. But unfortunately, the current state of the electrical grid around the world does not amount up to the expectations and calls for an urgent need for modernization. And this leads to the concept of the smart grid, which is basically the electrical grid of the future. But before exploring smart grids, we must first get to know what electrical grids are. Electrical grids consist of an interconnected network of power plants, electrical substations, distribution lines, and transmission lines. And the main purpose of the grid is to get power produced at the power plant to its consumers, be it industrial, commercial, or residential consumers. And not only that, but the grid must be able to manage, coordinate, monitor, and optimize the flow of electricity within the network. So the role of the grid goes beyond the simple transmission of electricity from one point to another. There are many components to the electrical grid, and we can mainly recognize two circuits or two networks in a typical electrical grid. These are the transmission and distribution networks, as you can see them in the picture. The transmission network transfers electricity from power plants to load centers via high voltage power lines. And the reason we use high voltage power lines is to reduce energy losses in long distance travel. The distribution network, on the other hand, is concerned with the local delivery of electricity to end users. So electricity leaves the power plant via transmission lines, then reaches local load centers where it is distributed by the distribution network. Along the way, there are several electrical substations, and their function is to regulate and monitor the flow of electricity at various points in the network. As a motivation for the importance of the transition to smart grids, we should consider the state of the current electrical grid, which, as mentioned before, falls short of expectations in terms of its capability to satisfy the electrical needs of future generations. This shortcoming is mainly attributed to the inadequate electricity management and distribution technologies employed in current electrical grids. Indeed, the current electricity grid is greatly outdated. And this is reflected by the fact that since the widespread of electrification back in the 19th century, no major developments have been introduced to the grid infrastructure established back then. So this aging infrastructure suffers from all sorts of inefficiencies, which lead to significant energy losses. And besides that, the whole conventional grid model, its topology, components, and basic operation does not match our current technological capabilities. So our current technological, the technologies that we currently possess allow us to have a much more developed grid. And this is basically the leads to the smart grid concept. To find a solution to this imminent problem, numerous attempts have been made to conceive an upgraded version of the electrical grid. This conceptual model of the upgraded grid has become known as the smart grid. And to be able to characterize the desirable features of the smart grid, one should first identify the limitations of the traditional grid that it's supposed to fill. The traditional grid suffers from many problems. Firstly, an aging and underdeveloped, underinvested infrastructure will certainly suffer from all sorts of inefficiencies, leading to substantial economic and material losses. Moreover, the centralized nature of the conventional grid, combined with its lack of monitoring capabilities, makes it vulnerable, since any local malfunction would be hard to predict and would affect a large portion of the network. Another issue is that the current grid suffers from its inability to accommodate a variety of energy production systems, such as renewable energy systems, due to the absence of the required technologies. In the current grid framework, these technologies can be accommodated, but this is a cumbersome process as special arrangements must be made to achieve that. Finally, the current grid technologies make it difficult for the electricity sector to transition to a new market model. The exact nature of this new market model will be discussed later in this presentation. We can now delve into the discussion of smart grids, starting with their definition. We present three different definitions here. starting with the definition given by the European Technology Platform, who defines the smart grid as an electricity network that can intelligently integrate the actions of all users connected to it, generators, consumers, and those that do both in order to efficiently deliver sustainable, economic, and secure supply. On the other hand, the US Department of Energy projects Grid 2030 envisions a fully automated power delivery network that monitors and controls every customer and node, ensuring two-way flow of information and electricity between the power plant and the appliance. Finally, the US Electric Power Research Institute defines it as the modernization of the electricity delivery system, so it monitors, protects, and automatically optimizes the operation of its interconnected elements, from central and distributed generator through the high voltage network and distribution system to industrial users and building automation systems, to energy storage installations, and to end-use customers and their thermostats, electric vehicles, appliances, and other household devices. As we can see, there is no universal definition of the smart grid. However, there is a consensus about the characteristics that it should have. The smart grid must be autonomous and intelligent, efficient, reliable, self-healing. It must be able to accommodate various energy sources and to allow a bidirectional flow of electricity. It should be able to create market opportunities and incentives. And finally, it must be sustainable and secure. Having identified these properties, we will indicate how the smart grid is able to achieve each one of these over the course of this presentation. Building on the characteristics of the smart grid mentioned just now, we will present the conceptual model of how such a grid should be structured and operated. First, the main distinction between the conventional and the smart grid is the decentralized topology of the smart grid. Unlike the centralized traditional grid, the smart grid is tailored for distributed energy resources, which consist of all types of geographically dispersed power generation, storage, and management facilities. An example of such facilities could be, for example, a solar power plant. And the advantage of this structure is that it consists of many densely interconnected nodes, whereby each node is a small to medium scale distributed energy resource, where energy is locally produced and stored. These local networks are entirely autonomous and independent, and they are known as microgrids. This dispersed structure of the smart grids is greatly beneficial. Some of its benefits are, for example, in terms of efficiency, energy losses in the smart grid are greatly reduced thanks to its minimized transmission distances and reduced grid congestion. So because we have multiple small to medium scale power plants, electricity does not have to travel over large distances to reach its end users. And as a result, we will minimize energy losses due to transmission and distribution. Also, local grid failures can be easily isolated, thereby protecting the remainder of the network, making it more resilient. For the same reason, because the grid is dispersed, if failure occurs at a certain point in the grid, it will not propagate further to affect the whole network, which is something that could happen in a centralized frame. So smart grids are expected to accommodate a variety of energy sources. This is especially important for the integration of renewable energies into the energy mix, which is one of the most important matters that the world is considering recently. Given that renewable energy systems are distributed in nature, the smart grid's decentralized topology is ideal for their integration. Moreover, the complex and intermittent nature of these sources is accommodated by the advanced smart grid controls and storage technologies. These technologies are part of the smart grid's advanced metering infrastructure, which allows for a bidirectional flow of electricity. That is, in smart grids, electricity does not only flow from utility to end users, but it can also flow from end users to the utility. So electricity consumers can now produce electricity and export it to the grid. And this is one of the most important features of the smart grid. Okay, so aside from renewable energy resources, the world is witnessing an unprecedented phenomenon of electrification and automation, from electrical vehicles to the concept of the Internet of Things and smart appliances. Hence, in addition to its ability to integrate modern energy production systems, the smart grid must accommodate the smart devices and appliances, which is something essential for this electrification. Within a local microgrid, such smart systems can work together to autonomously optimize local energy use and maximize utility. At the same time, these local systems would all be connected to the smart grid, exchanging both electricity and information. This allows the smart grid to extensively monitor energy flows at all points within the network, which offers a limitless range of capabilities. For example, this configuration allows the smart grid to take demand-side measures to achieve a smooth and efficient grid operation. In addition to that, under this framework, the smart grid employs state-of-the-art data analysis and forecasting algorithms to autonomously predict load patterns and allocate the respective energy resources at its disposition in the most optimal way. So by connecting to local microgrids, the smart grid can manipulate energy consumption in a way that optimizes energy flows and is beneficial to both consumers and the utility. As pointed out before, the smart grid transition is driven by a transformation of the electricity market. Classically, electricity is produced in mass amounts by government-owned utility power plants and is then sold to end users. But under the smart grid model, the role of the electricity consumer is transformed. Thanks to the smart grid's distributed structure, end users can now produce and sell their own electricity via privately owned distributed energy resources. And this allows private parties to enter the electricity market, making the market much more competitive. In addition to that, this framework encourages private parties to invest in renewable energy projects, which is something that is very desirable in terms of environmental objectives, satisfying environmental objectives. In conclusion, this novel electricity market model contributes to making the energy sector more sustainable, more competitive, and more secure. Finally, to conclude the section and to highlight the advantages of the smart grid, it is useful to compare it to the conventional grid. Firstly, in terms of technology, the smart grid is fully automated and digitized, whereas the conventional grid is mostly manually controlled and mechanically operated with the aid of very basic technologies. Secondly, while the flow of electricity in traditional grids is solely from utility to consumers, the smart grid allows for a bidirectional flow and thus for consumer engagement in the electricity market. This is what we've been talking about in the previous slide. In terms of architecture, the smart grid's decentralized and dispersed structure is far superior to the conventional radially connected model, which is very beneficial as we showed before. As for monitoring capabilities, the smart grid's huge network of sensors enables it to closely supervise grid activities at all grid nodes, something that is unavailable in traditional grids. Also, because of the advanced technologies employed in smart grids, the response to external disturbances is much faster than the response of the traditional grid, which would require which would involve human activity, in contrast to a fully automated response in smart grids. Nevertheless, this digitization and automation has some negative features. Most notably is the increased susceptibility to cybersecurity threats, and this is something that we wouldn't encounter in a conventional grid. And this is one of the main obstacles to the development of smart grids, which will be discussed at the end of this this presentation.
Okay, so concerning smart grid technologies, we're now interested in providing an overview of the technologies that allow it to achieve the discussed functionalities. Starting by the multi-agent control, smart grids involve a huge number of autonomous systems working together. So it relies on a decentralized control scheme called multi-agent system that is subdivided into multiple layers. The lowermost level is that of process control, which ensures a smooth functionality of the individual DERs. The next level is plant control, which relies on power electronics. The structure is called supervisory control and data acquisition, SCADA. SCADA is well established in modern industry as it ensures the continuous and autonomous operation of the plant. The main role of the supervisory unit is to collect and analyze data streams incoming from all smart grid nodes in order to issue the control commands. Next. Concerning fault-tolerant control. Fault-tolerant control, as also called FTC, is one of the pillars of the smart grid that gives it self-healing properties. It is a subfield of control theory that is concerned with ensuring that autonomous systems are resilient to operational faults. FTC employs a large body of sensors that collect massive amounts of data. This data is processed and then examined in real time by fault detection computer models. If faults are detected, suitable mitigation protocols are automatically initiated. These corrective actions are ideally supposed to successfully isolate, alert, and automatically repair malfunctions when possible. The major advantage of FTC systems is their ability to crunch huge amounts of data and to make conclusions based on that. Communication. Next. We know that components of the smart grid must be linked via modern communication technologies. Within microgrids, data is exchanged via wired local area network technologies, such as Wi-Fi and Ethernet. On the other hand, information flow between disruption networks is ensured by power line communication technologies, PLC, especially broadband power lines, PBLs, and wireless telecommunications such as radio frequency meshes and various generation cellular services such as 3G, 4G, and 5G. As for long-distance transmission networks, reliance is on optical fiber communications. Next. Sensing and measurement. Perhaps all of smart grid functionalities require access to massive amounts of data. This makes sensors one of the most essential components of the smart grid. Since electrical grids are mainly concerned with the quality of the transmitted power, smart grids are equipped with cutting-edge synchro phasers and phasers measurement units, PMUs, which are high-speed voltage and current measurement devices. Such devices are essential for real-time monitoring of grid conditions, as they can be up to 10 times faster than conventional phaser sensors employed in SCADA systems. Besides supervising power quality, smart grid sensors have numerous applications ranging from basic alarming to full condition diagnostics. Next. Data management and decision making. Immense volumes of data are generated by smart grid sensors. For this information to be useful, it must be managed, stored, processed, and then analyzed. The first step is data collection, which is the job of the grid's data loggers. The raw data must be then pre-processed before storage. Also, before storage, data coming from different sources must be integrated together in a compatible way using standardized information models. We now come to the matter of the data storage using the simplified mandatory access control kernel framework called SMAC. Once information is properly logged and readily accessible, analytics can be performed using sophisticated computer software that employ trained machine learning models to detect patterns in input information. Next. Information systems and simulators. Given the great complexity of smart grids, it is desirable to provide grid personnel, service providers, and other actors with efficient and effective tools for monitoring and planning operations. Various software solutions are designed for optimal accessibility and ease of use, as they have interactive user interfaces that present complicated information in a clear and understandable way. Another important matter is smart grid modeling and design. So before any smart grid can be implemented, one should attempt to prove the viability and benefits of the project. Next. Integration of DERs and the advanced metering infrastructure, AMI. As discussed before, the integration of DERs in the electricity market requires the existence of a supporting infrastructure. So the first requirement is the presence of the basic control and energy conversion and storage systems. In addition, enabling private energy production and thus two-way electricity flow requires the establishment of an advanced metering infrastructure called AMI. AMI is a collection of systems that collect, manage, and analyze data coming from individual smart meters located at the microgrid level. In addition, the AMI enables both the smart grid and its end users to remotely control microgrid subsystems. The meters employed in the AMI are smart meters, which are devices that can perform three main tasks: keep track electricity flow data, remotely control microgrid appliances, and remotely manipulate electricity consumption. Traditional meters can only accomplish the first of these three functions. Next. Okay, the AMI architecture is a multi-layered architecture. As we can see, the lowest level is called the Home Area Network, HAN, which consists of a local network and residential homes. The second layer is the Neighborhood Area Network, NAN, which connects the multiple HANs located within a given region to a distribution station, which controls electricity supply. And the final layer is the Wide Area Network, which is the backhaul network of the AMI, connecting core communications and central and control centers to the grid edge components. Next. Demand response. Demand response is a set of passive or active demand-side instruments that aim to modify electricity consumers' behavior. The main purpose of demand response is to defer electricity consumption from peak hours to off-peak hours, thereby achieving significant economic and environmental benefits. There exist various demand response tools classified in two categories: incentive-based programs and price-based schemes. Incentive-based programs such as direct load control or DLC are based on the premise that by providing consumers with means to reduce their energy consumption, they would opt for these alternatives, and that would imply making monetary savings on their utility bills. On the other hand, price-based instruments rely on manipulating the prices of the electricity. So by increasing the price of electricity during peak demand hours, consumers will naturally tend to reduce consumption. So the smart grid plays three critical roles: monitoring, forecasting, and establishing real-time communication. For example, if demand is expected to be higher than usual during a certain period, measures can be taken beforehand in order to cope with the higher loads. Thirdly, the smart grid's communication infrastructure ensures real-time communication between customers, their hands, and utilities. This way, pricing can be done in real time, and consumers can be instantly notified. Now, concerning security, since everything is digitized and automated in the smart grid system, serious cybersecurity and privacy issues arise. Vulnerabilities should thus be eliminated by implementing suitable security protocols. It is an interesting thing to note that most security issues in smart grids come from smart meters. These technologies are very attractive to hackers since they are more vulnerable than other systems and can be accessed with less cost and experience than for other technologies. One way to solve this problem is to make power suppliers echo the energy readings they receive from smart meters back to the customers so that users can verify the integrity of the smart meter, which can decrease the number of attacks and leaks in the smart meter system. Next. Challenges to smart grid development. There are many challenges that must be overcome when going from conventional to smart grids. These challenges can be technical or non-technical in nature. Starting by the stakeholder engagement. Since the implementation of the smart grid requires the engagement of the whole community, from policymakers to industrial players to end users, it is necessary to get all these actors on board for such a major reform. Secondly, high initial costs. The implementation of smart grid involves substantial capital investments, and its components are mostly high-end devices and systems that have high initial costs. 3, renewable energy resources. One of the main advantages of the smart grid is its ability to incorporate renewable energy sources into the electrical network. However, the transition toward the renewable energy sources face certain complications itself. For energy storage technologies, the smart grid relies heavily on energy storage technologies in its autonomous functionality. Like renewable energy sources, these technologies are still not fully mature and are rather costly. As we already said, the prominence of information technology and digitization at the heart of smart grid's function introduces various cybersecurity concerns. Concerning privacy, and since smart grid devices collect large amounts of personal data, consumers will be concerned about how this information is being handled. Next. We have discussed earlier how the concept of smart grid emerged out of the need to improve the electric grid and to fulfill its limitations. The modernized electrical grid matches the technological capabilities of the century and gives rise to a novel electricity market where the role of the consumer is redefined. Besides offering new possibilities, the smart grid enables a much more intelligent, autonomous, efficient, and resilient electricity sector. To make that possible, the grid integrates a wide array of technologies in a densely interconnected network. However, many challenges are yet to be overcome to witness a global transition towards the modernization of electrical grid. Thank you. Do you have any questions?
Thanks for listening.
Okay, thank you, guys. I will open a new meeting to continue, okay?
Okay.
Okay.